Okay, so last time we finished with defining the normal bundle to a subvariety and giving an interesting exercise to it. So that I think is an exercise you should try to do. That was actually something to do. You have to see it. But now we will talk about another object which is somewhat related to subvarieties. These are called Cartier Divisors. For now, we will only talk about effective Cartier divisors. We will see what is a general Cartier divisor in a bit. So this is only defined, or well, technically, I guess it's defined also in the real case, or you can say that it's defined or interesting. It is only this on complex manifold. Okay, so this is an object which is only defined complex manifold, in principle also on real manifolds, but then there it doesn't really make sense. It's not interesting there. So let's define it. So M complex manifold. Then an effective Cartier divisor. D on M is given by an atlas U alpha and holomorphic functions F alpha from U alpha into C, which are not identical to 0. They can be constants, but not 0. And they can have zeros, they're just not identical to 0. And such that if the intersection between two of these open sets is non-empty, then they map F alpha beta, which we define as F alpha divided by F beta, as a map from U alpha intersected U beta into C, is also holomorphic and without zeros. So this is basically equivalent to saying, so F alpha and F beta have the same zeros with the same multiplicity as well. Same multiplicity. So, because normally when you take the ratio of two holomorphic function, what you get is a meromorphic function. So what we're asking here is that this ratio is actually a holomorphic function. So whenever f of beta is zero, f beta is 0, also f alpha is 0, and actually the multiplicity cancels out. So, I mean, asking only holomorphicity is just asking that the multiplicity of f alpha is greater than the one of f beta, but we're also asking without 0, so we're actually asking the same. This is the same actually as asking that not only f alpha beta, but also f beta alpha is holomorphic. Okay, so this without 0 is perhaps a bit redundant, because we're asking for every alpha beta such an intersection is not empty. And as exercise, very easy exercise, you can verify that this maps here verify the cocycle conditions. So these f alpha betas are maps into C star, basically because they have no 0. So you can think this as maps into GL1. So GL1 will be C star. So since they verify cocycle conditions, they define a complex vector bundle, holomorphic vector bundle of rank 1. So we have some maps defined on some intersection, and they verify Gauss conditions, so they give rise to a bundle. And this bundle, we call it OD. And D stands for the divisor. Okay. And furthermore, so we had so this is a bundle, and these F alphas are the local data of a section of OD. Because remember, we said that something is a section. So this F alpha is the local dot. So this F alpha is the local dot of a section. If you have that F alpha is equal to F alpha beta times F beta, but this is true because this is nothing but F alpha divided by F beta times F beta. No? So they glue together. So this is the local dot of a section already. So now we can produce with this observation, we can produce a vice versa. So it's not true that given a vector bundle of rank 1, a holomorphic vector bundle of rank 1, you get immediately a Cartier divisor. But if we're given a rank 1 complex vector bundle, these are usually called line bundles because this is a complex line. So if besides the complex one vector bundle, we also give a global holomorphic section of it, then the local data of the section determine a Cartier divisor. Okay. So this is to say that you should imagine this Cartier divisors, which in principle are just these collections of F alphas, as basically sets of zeros of global section of some line bundle. So now let's see something which is a bit more similar to an algebraic construction. So another way is to look at complex submanifolds of codimension 1. So codimension means, okay, if the manifold has dimension n, then a complex submanifold has codimension 1 has dimension n minus 1. So let S be such a submanifold. Such a submanifold. And let's take an atlas adapted to it. An atlas of M adapted to S. So let's recall what this means. It means that if you look at S intersected U alpha in the intersection and you apply phi alpha, but this is something that you kind of never write. So here we write equal, but usually when you intersect with a chart, what you mean is after applying the chart. So the proper way to write this would be to say phi alpha of this, it's equal to this, right? But this is often dropped because that's always a homomorphism and that's just things are done. And you see now that on U alpha intersected U beta, the last coordinate here is 0 if and only if the last coordinate of the other one is 0. This is simply because the manifold S is defined everywhere, and this local chart is adapted. This atlas is adapted everywhere. So if now we think Zn alpha as a function of the other variables in respect to beta, so you should really think of this as the transition map, the last coordinate of the transition map. So of the last coordinate of phi alpha inverse composed phi beta. No? Well, since they need to be 0 at the same time, this must be some Zn beta times another function, which is non-zero. Not right here. For some u, which is holomorphic and non-zero on u alpha intersect u beta. Okay. But one thing that we do know is that this composition is indeed transition map. So we look at the determinant of the differential of this transition map. And we know, of course, this is non-zero. But we also want to compute it kind of explicitly. So here you have the derivative of z1 alpha with respect to z1 beta. No? Here you have the derivative of zn alpha with respect to zn beta. Here you have dz1 alpha with respect to dzn beta. You have dzn alpha with respect to dz1 beta, etc. So this is a squared n minus 1 times n minus 1 matrix. Here we have a n minus 1 dimensional vector, n minus 1 dimensional vector. This is just a number. Well, we know that this is non-zero at every point, right? Because it's simply the determinant of a transition map, which are diffeomorphisms, so they're non-zero. Actually, bilomorphism in this case. Okay, so this is non-zero, but on S and only on S, all this row here is 0. And j from 1 to n minus 1. And the reason for this is that we know that the last coordinate is 0 if and only if, so the last coordinate with respect to alpha is 0 if and only if the last coordinate with respect to beta is 0. So this thing that you're doing at the, you like this function, n minus 1 beta, and here you have 0 because we are on S. And we know that this is identically 0 as a map in n minus 1 variables, right? So when you take the derivative with respect to one of these variables, what you get is, of course, 0. So when you restrict to S, this is what you're doing, really. And this is the identically 0 function, so this is not necessarily 0 whenever we leave S, because then here you're going to have something else. But on S, for sure, this is true. Okay, so now we can use this formula again. So yeah, sorry, in particular, why did I care about this? Well, because this is telling us then that Zn alpha with respect to Zn beta, P is non-zero for every P in S. Because of course, if it would be 0, then the whole row is 0, and then this doesn't work. Okay, so we have this information, but we also have the other information. So we can actually compute the derivative. And what is the other information? The other information is this one. We know that Zn alpha is Zn beta to the k times u for some k greater or equal than 1. So we take the derivative, And well, we derive the first term. I'll rewrite it. This Zn beta to the k minus 1 times u plus Zn beta to the k times the derivative of u with respect to the Zn beta. Yeah, we just derived using the standard Leibniz formula. But now we see what we know, that on S, this is never 0. And S is precisely Zn beta equals 0. Okay. So on P, basically this is always, sorry, on S, this is always 0. And this is always 0 unless k is equal 1. So we must have that k is equal 1. And the u is non-zero, S. And actually u, if we go back here, u is nothing but Zn alpha divided by Zn beta. And we know that this is never 0 and holomorphic. Because we knew that u was never 0. So u in u star.
One question. So was the if you go back to the final slide, was the trick that the second part plus yeah, that part has to be 0 due to something, or
Yeah. So okay, try to put p here
mhm.
and take p in S. So basically
Yes.
what you're saying, let's take Zn beta equals 0.
Hmm.
So okay, you evaluate, and here you have do it in a different color. So you have p here, and this is equal to 0. So this whole term disappears.
And why is it 0? Why was it 0?
Because this p is in S. And S is precisely Zn beta equals 0.
Yeah. Okay.
So
Okay.
since
Great.
k was greater or equal than 1, this is 0. And then we know that
Okay.
the whole thing cannot be 0. So in particular, k must be 1.
Yeah. Yeah. Then I got it.
Okay.
Thank you.
And u is now 0. Okay, so we have this function here, which is defined only in the intersection, right? So this is never 0 and holomorphic. So the data Zn alpha is a Cartier divisor, an effective Cartier divisor, which we call square bracket of S. Because remember, Cartier divisor is just a set of function of alpha such that the ratio is holomorphic and without zeros. And here we have them. Zn alpha is defined on u alpha. Zn beta is defined on u beta, but when you look at this ratio on the intersection, is never 0 and holomorphic, so it defines an effective Cartier divisor. And we have something more on S. On S, remember that this Zn alpha over Zn beta, if you restrict it to S, this is the same as the function u restricted to S. But when we restricted this whole thing on S, so if you look back at this formula, when you restrict it on S, you're basically left with this derivative equal 1 times 1 times u. So u is actually the derivative. It's not only the ratio, but it's also this derivative. Only on S. Clear? Just look from here. I mean, just look at this formula with k equal 1. And normally you have this remainder term, but when you impose it to be equal to 0, so when you're an S, you're left with just this. Why do we care about this? Well, because we said that the Cartier divisor defines a line bundle. Yeah, holomorphic vector bundle of rank 1 with transition functions given by this f alpha divided f beta. So if this U is our F alpha beta, but we know that is also equal to dZn alpha and dZn beta. And if you remember from the definition of normal bundle, this is precisely the transition functions of the normal bundle to S. I hope you remember that. So the normal bundle to S is precisely this holomorphic line bundle associated to S, restricted to S, because this is defined only on S. Well, this is defined on the all of the manifold. Okay. Why are they the same? Well, because I mean, let's say it's morphic, because they have the same transition function. No. And another observation is that these F alphas, so the local data, which in this case are just Zn alpha, are 0 to order 1 on S and nowhere else. Okay, so we have this kind of three-way intersection between Cartier divisors, line bundles with a global section, not just line bundle, but we need a line bundle with a given global section, and sub-manifolds of codimension 1. Why codimension 1? Because then the normal bundle basically has rank 1. Okay. And it turns out that basically they're all the same thing, more or less. So this is to say that we can think as this OS that we define this way a bit, seems a bit artificially. You know, we like, oh, we have a submanifold S and we have this Zn alphas, which define our submanifold S. And if we take the ratio, it turns out that these are the transition function of some bundle. And they're like, okay, let's call it OS. So this is a bit okay. But then we realize that this is, you can think of this as an extension of the normal bundle to the all of M, right? So this is OS and it's defined on the all of M. But if you restrict it to S, this is the normal bundle. So you can simply think that this is an extension. So the normal bundle is defined only on S, but if you want to extend it, this is perhaps a way to do it. Okay, now we're gonna get into more, I'm gonna call it algebraic things. Because when we have, now that we have vector bundles and we have maps between them, of course we're interested in studying the kernel of these maps, the images of this map. And all of this can be resumed in what I think, but you're gonna tell me if it's a new topic for you or not, and it is exact sequences. Have you ever heard about exact sequences?
Yeah, they are very familiar.
Okay, perfect. Oh yeah, maybe a small so have you ever heard of divisors before? Probably in some algebraic geometry course.
Yeah, actually, I heard once of them, but only for like 1 week.
Okay. Well, if you heard it in algebraic geometry course,
Hmm.
they also have the standard way. Yeah, you start with a submanifold, you associate this thing, and this gives you a bundle. But just by the way, I mean, they define it a bit differently. And so if you come from algebraic geometry,
Yeah.
this what we defined as this. So our is the algebraic geometer's inverse of this, dual of this.
All right.
Just basically instead of taking Zn alpha over Zn beta, I take Zn beta over Zn alpha.
Mm-hmm.
Just remember, this is just inverting, no? Just a small disclaimer, so if you see it somewhere else. Okay, so to talk about kernels, we need, of course, two vector bundles over M and a morphism. of vector bundles, of course. And this phi is basically is a section of something we discussed, which is the vector bundle of homomorphisms from E to F. Okay. So what it means is that over every point, what you have is a linear map between EX and FX. So the proposition here is that the kernel of phi, which is a subset of E in principle, and the image of phi, which of course are defined pointwise, no? So the kernel of phi is the thing, is the union of kernel of phi x for every x. Same for the image. This is also in F. And the provision that they are subbundles. Not always, but if and only if the rank of phi x is constant. Okay. Proof. Well, one direction is trivial. Because if you are a subbundle, then at every point you have the same rank. So good. Well, let's see the other direction. So okay, rank x is constant. Let's call it k. And let's give also names to the other ranks, m and l. So sometimes you might be tempted to call this not the rank, but the dimension of E, right? Careful, because when we talk about the rank of a vector bundle, we mean the dimension of the fiber. But when we talk about the dimension of a vector bundle, we remember that this object is a manifold, so it's the dimension as a manifold. That's why we use a different name. Okay, so to prove something is subbundles, we need to find a local trivialization. Okay, so we do. So actually, even before a local trivialization, we have to prove that it's manifold, I guess. Trivializing open set for E and F. So in this trivialization, phi, you can think of it as a map from U times Rm, U times RL. And here again, I'm like, when you have a trivialization, you have your psi alpha, psi beta, and here I should pre-compose and post-compose with psi alpha, psi beta, no? To actually be here. But again, this is usually skipped. And we simply think of phi directly in the trivialization. Okay? And this is going to be given by some expression. So we take xa, and a is a vector in Rm. Well, this is going to be 2x, because this is a vector bundle morphism. Xa, and a is something in Rm. While a, you can think of it as a map from U into the set of matrices from M times L. Yes. L times M times M. Maybe L times M. And since we're assuming that the rank is constant, let's say we fix an x0 in U, and the rank of a x0 is k, because no, the rank is k. So this is the rank as a matrix. And by continuity, sorry, no, that's not what I meant to do. Not yet. We're not talking about continuity yet. The rank is k, and so we can assume that the first k rows are independent. Doesn't need to be the first k. We just, we have k rows which are independent. Well, we can assume they're just the first ones. We can just permute the coordinates. And then now by continuity, the first k rows of AX are independent for X in, well, technically not in U, but we can restrict U, okay? And what I mean by continuity, well, you know that first k rows to be independent means that some minor is non-zero, right? So if you're non-zero at a point and minors is an algebraic operation of the entries, this is a continuous map. So I don't know if you've ever seen this argument before, but yeah, if you have some independent vectors, what basically means is some determinant is non-zero, and you know if you're non-zero at a point, then you're also non-zero in a neighborhood because everything is continuous. Okay. Okay, so now we separate these rows. So we take Bx to be the k times m matrix. Wait, am I? Yeah, k times m. Such that Ax is basically this Bx on top. So this is the one with the k independent and something here. Okay, this is the k rows. So B is just the matrix of the first k rows. But since they're independent, and not only independent, but they generate everything, because the rank was exactly k, the kernel of phi, you can write it as all the xa in u times rm, such that bx of a is equal to 0. So the kernel normally here we would have capital A, x of a is equal to 0, but since this generate everything, it's enough that these ones are 0. And why do we care about this? Well, because then this is a kind of maximal rank anyway. And this lets us use the implicit function theorem. So let's define a function which will be useful to apply the implicit function theorem. Yeah, so we're sending x and a to b of x times a. And if we compute this differential, here you get something, which are basically the derivatives of b with respect to x. But here you get b of x, because this is where you derive with respect to a. So it has rank at least k, right? Because this part is rank k, and then maybe we get something more here in principle. But k is the maximal rank simply because we're going into our k. Yeah. But now this implies that the inverse image of 0 is a submanifold. Correct, because this is simply the implicit function theorem. If you have a function of maximal rank everywhere, then the anti-image of a point is a submanifold. So this proves that this kernel phi is a submanifold of E. Okay, not a subbundle yet, but definitely a submanifold, which is a requirement to be a subbundle. So now we want to, so this B is not a square matrix, right? So we take B prime and B second such that B of x is B prime of x, B second of x, and b prime of x is GLK. See. So basically what I'm saying here, okay, we know that the B is of rank K. In particular, he has a minor, a squared minor, a K times K minor, which is non-zero, right? And I'm just assuming that this minor is the one made by the first K columns, okay? And we already knew it was K times M, so this actually takes everything. It's not just a square, but it's really half of the matrix. And it's never zero. And this is an assumption. I mean, again, we can just permute coordinates. Okay, for every x in this neighborhood here. And the same thing, we separate A into A prime and A second. So we think of this as an element of Rk times Rm minus K. Okay. And why did they do this? Well, because now you see that Bx of A is equal to 0 if and only if B prime of x times A prime plus B second of x times A second is equal to 0, which gives us, since this is invertible for every x, it gives us this nice expression where A prime, so B of x is equal to 0 if and only if A prime is this function of A second, an x. In particular, this gives us M minus K independent solutions. Yeah, you can take this one to be a basis for M minus K, for Rm minus K, and then this part is given to you by this formula. So we have A1 A M minus K independent solutions. Okay. And they generate the kernel. Sorry, it doesn't fit in this corner. So what do they generate the kernel? Because remember this Bxa equals 0 is precisely the kernel. Okay. So if you kind of forget just x, what we're looking for is a basis of this kernel. And kind of you can just forget that all these matrices depend on x. You say the kernel is B of A equals 0, and then you need to find the basis. And in this way, you see that this is like the independent variable and this is the dependent variable. The only thing just now, once we have this formula, you kind of have to remember about x, because you know when we have sections, so this you should think of them as sections, independent sections. When you have sections, you need them to depend holomorphically on your x, or smoothly, depending on the category. In this case, smoothly. And this whole operation depends smoothly on x. Okay, see, this is clear. This one is because the inverse actually does depend smoothly on the entries of B prime, right? So if you have a matrix, the operation of taking the inverse is a smooth operation in the entries. You can think of this because, I don't know, GLK is a Lie group. So taking the inverse, it's a smooth operation. Okay. Okay, so these are solutions of curve phi, but these are written in this trivialization, no? So they generate curve phi on you in this particular trivialization. So let's say that we apply our trivialization. So here J goes from 1 to M minus K. Be the image of AJ. X is A. under this realization. Yeah? So they're basically just AJs themselves. We complete it to a basis. So we have the first m minus k, and then we add some m minus k plus 1 of x, comma, the m of x e over u. Okay. So why are we doing all of this? Because remember, what we had to prove is to prove that curve phi is a subbundle. So what we have to do is basically find the local trivialization where the kernel of phi is precisely, it's like fiber-wise a subspace. And so we built this new basis of E, and if you remember, constructing a basis of E is the same as giving a trivialization, and we'll actually do it just now, such that the first m minus k vector generate the kernel. So a new trivialization is, so you have an element here, you can write always at bj times vj of x. So this is an element of ex. This is a basis, so there's only one way to write it. And the new trivialization sends this to x, comma, b1, bm. And in these new charts, this new trivialization, the kernel of phi is precisely made of those vectors such that the last m minus k coordinates are 0. Yeah, because remember, the kernel is pointwise generated by this first m minus k. So if all these are 0, you are in the kernel, and vice versa. Hence, the map, the same map basically, but we only go to m minus k. It's a trivialization. Trivialization for the kernel. Yeah. And okay, technically now there is one thing left to prove. So we have this local trivialization. We have to prove that when we go from one into another, the map is an isomorphism, is a pointwise isomorphism of vector spaces, right? So exercise. Prove that this trivialization makes Kerfi a vector bundle. Okay. So any questions about this? No? Okay. Well,
It's good.
okay. Yeah. If you forget about X, this is just linear algebra basically. And the only times where you have to remember about X is when you have to prove that everything depends smoothly on X. At some point you have to say it. And I guess this is the only moment where it really matters. And otherwise, once you're done with this linear algebra, what you have to do, yeah, is this exercise. So basically also prove that everything is somewhat independent of change of coordinates. This is basically what we're saying. Okay, so now for the image, and it will look weird that I start in this small space, but it's actually enough. So we take Q to be the quotient of E mod curve phi. Yeah. And then our regular most mean EF induces a morphism on the quotient, Rho, right? And this is injective on the fibers. And surjective not on F, but of course on the image of phi. Okay. And if you remember when we defined what is a subvector bundle, we asked that there is a vector bundle such that this subvector bundle is the image of under an injective map. This was the definition of subvector bundle. You're the image of a vector bundle under an injective map. But now we know that Q is a vector bundle and you're the image of Q under an injective map. So image of phi is a vector bundle. Okay. So the image not just of a not just the injective image of a vector bundle, but the injective image of a vector bundle via a vector bundle morphism. Because otherwise you lose all the structure. Okay, so now that we have a notion of an image and kernel, and not only we have a notion, but we show that this notion is compatible with all this category of vector bundles, we can talk about exact sequences. So we have a manifold. We have E prime, E second prime, vector bundles over M, and take alpha from E prime to E and beta from E to E second, morphisms. So morphisms, of course, of vector bundle. And we define that if alpha is injective and beta is surjective, and the bundle image of alpha is equal to the bundle kernel of beta, the sequence 0, E prime, so this is just the injection, alpha, E, beta, E prime, E second, 0, is a short exact sequence, is a short exact sequence. Okay. And observation, if we have such a short exact sequence, then the last bundle is just the quotient of the first one. Yeah, because it is surjective and this is injective, so you can think of E prime as a subbundle of E, and basically by the last proof, you get the same. There is also so-called rank formula. So prove that the rank of E prime plus the rank of E second is the rank of E. Okay. Now what I want to do is produce new short exact sequences from old ones. So proposition we start with such a short exact sequence. And we take F, another vector bundle, again over M. Then the following are also exact. And we have quite a few. So you can tensor the whole sequence. With F. So we defined some time ago the notion of tensor, product of vector bundles. And of course, I have to tell you what the maps are. Well, you take the map A tensor identity, and here you take beta tensor identity. Okay, so we also know what is the tensor product of two maps between the tensor product of the respective spaces. Also, if you take hom from F into E, this is also exact. Zero. And here the maps is given by post composition. Yeah. So, I mean, is the standard way to do this. You can also switch the order. So if instead of having a homomorphism from F to E prime, you take from E prime to F, what happens is that you actually reverse the order of the objects. So homomorphism from E second to F into homomorphism from E to F into homomorphism from E prime to F. And here because here you're pre-composing. That's why it switches direction. Yeah. Again, this is the standard way to define these maps. So this can be reassumed in saying that tensoring with something or is an exact, it's what is called an exact functor. I don't know how much you know about category theory. No?
Yeah, that's I know a lot about that.
Okay.
So is that to say that wait a second, every vector bundle is projective or no?
I don't know what that means.
It means that doing the hom functor with it preserves exact sequences. But now that I thought about it, I don't think that's true because we need the exact sequence to be the special one in the category of vector bundles. Okay, so
No, I mean,
that was stupid.
oh, because you're thinking of long exact sequences in general.
No, short
Or
exact
short one.
sequences.
Yeah, I mean, if you're in the category of vector bundles,
Yeah.
then yeah, the homomorphism functor is an exact functor. Covariant or contravariant based on
Yeah, of course.
what you care. The big importance of this last row, I mean, of course, this is more general, so it's more important, but it's worth observing. If we take F to be the trivial bundle of rank 1, no? We get the dual, no? The dual maps here.
Yep.
And notice that the dual is contravariant, so you switch the order. No? There is one more. Oh, I didn't save space for it. So further more. If F from N to M is smooth, also this is exact. 0 goes to F star E prime F star E. F star. Second. So the pullback is again covariant exact functor. So the proof is a beautiful exercise. So I would say this is one of those exercises which is, I mean, to do this now would require maybe an hour to check all of this. So this is one of the exercises you give because you don't want to use an hour to just do more linear algebra. Okay.
So it's tedious, but not very insightful.
Yeah, I would say that.
Okay, yeah, good to know.
Yeah, because I mean, no, you really don't have to check anything. I mean, because the fact that these are vector bundles, we know already. Just to check that the kernels stay the same and that the images are good. So yeah, it is a good exercise for later. At some point, having done some of this will be useful when we'll talk about sheaves. But we'll do plenty of that when we'll do sheaves, so it's not essential. So let's say that we have a short exact sequence. Okay, we know from the previous position that we can make new sequences, but what information can we get out of it? For instance, we get some information about the correspective determinant bundles. So if you remember so if you have a vector bundle, you have your transition function G alpha beta that respect the ecocycle condition. Then also the determinant of G alpha beta satisfies the ecocycle condition. And therefore it defines a line bundle. And this line bundle we call determinant bundle. Okay, defined this I think 2 weeks ago. And what you get is this formula that the determinant bundle of the middle one is the product of these two. Let's prove it. It's not too hard, but yeah, this is a bit more insightful, I think. So we take an atlas of E adapted to alpha E prime. Yeah, this is an injective map, so you can think of this as a bundle. Then the transition maps for E, we can write them as a block matrix, and here we have the transition maps for E prime. Here we have just something. Here we have zeros, and this is because it's adapted. And here we have something which we know satisfies the. So here we are the ones from the quotient bundle. Yeah, here we would have E divided E prime. But we know from here already that E divided E prime is nothing but E second. So this is the transition functions of E second. And now it's trivial. Because you take the determinant of this is a block matrix. So the determinant of the block matrix is the product of this determinant times this determinant. Okay. And this is precisely the transition functions of the bundle determinant E prime times determinant E second. Okay. So let's go back to complex manifolds, because all these things that we're doing are actually more studied for complex manifold and they're more interesting for complex manifold because mostly you have more rigidity. So you can't just do whatever you want. So if you have a complex manifold, we can consider its tangent bundle, its cotangent bundle, and then take the determinant bundle of that. This has a special name and is the canonical bundle of Very, very much studied. Yeah. Now I want to give you an observation. So let's take a line bundle, L, line bundle. So for instance, this KM. If you take L tensor L star, this is, we know, the homomorphisms from L to L, correct? In general, homomorphism from E to F is E star times F, no? But this object here admits a global section. And which one is the section? Well, homomorphism from L to L, you just send X to the identity over X of LX. But we know that if a vector bundle admits a nowhere zero global section, then it is trivial because this is rank 1, right? This is nowhere zero and dimension 1, so it's trivial. So L times L star is equal to M times C. So you can think of this taking the product. If you think about it as an operation, you're basically saying that L inverse is L star. Okay, if it makes sense. And actually, if you take any two other vector bundles, E and F vector bundles, not necessarily rank 1, then E tensor L is isomorphic to F if and only if E is isomorphic to F tensor L star. And what's the reason for this? Yeah, you go back here, you multiply, so you tensor with L star, and basically what we're saying is this L times L star cancels out. And the point is that it does because it is isomorphic to M times C. So if you really think about it at the level of transition functions, the transition function for M times C is just the function which is always 1. So it definitely doesn't influence E. So we get back E. So E tensor L star is E. This is what was written here, basically. Okay. Now we have a theorem, which I think is going to be the last one from today, which is going to basically link all we did today. So we take a complex submanifold of codimension 1. So what can we do with it? Okay, we know that to it we can associate a Cartier divisor, hence a line bundle. Okay. And what we're going to give now, it's a relationship between the canonical bundle of S. So remember, this is the determinant bundle of TS star. So it's a bundle over S and only over S. This is the same as taking the canonical bundle of M, then tensor it with this line bundle defined by S and restricted to S. Because again, these are bundles over M. This is only over S. So you have to restrict it. Okay, so I think for now, this maybe just looks like, okay, it's some formula which I don't really understand. But again, the interpretation of this is that you have this canonical bundle, which for reasons which you don't know yet is important. And you can think of this KM tensor OS as an extension, the all of M, of the canonical bundle over S. This is what this formula is saying. And this taking this tensor part is usually called the twist. So you can say that the canonical bundle of S is a twist of the canonical bundle of M. and the twist is given by this line bundle we defined. And maybe when you look at this, you might think that the proof should go through something ugly, let's say, or very hands-on, like taking transition functions and just find out that the transition functions are the same. That would be my first idea. But now we have this beautiful setup of exact sequences. So I hope this becomes more clear by looking at the proof. This I think is really one of this proposition will looks better once you look at the proof. So we start with this exact sequence. So what's this exact? Simply by definition, how we defined this normal bundle. We defined it as the quotient of Tm restricted to S divided to S. So this is an exact sequence, but be careful because this is only exact over S. Okay. And well, eventually we want to reach something which relates to Ks, right? So ideally we want to dualize and then take the determinant. So let's start by dualizing. Dualize and you get n star S, T star M restricted to S, T star S. Results exact. And now, as we were saying, we can take that formula that we said before, which relates the various determinants, this one. So the determinant of the middle one is the product of the external ones. So the determinant bundle of T star M restricted to S is the same as the determinant bundle of N star S tensor the determinant bundle T star S. Okay, so let's rewrite it with these new names that we gave. So the determinant of T star M on S is nothing but Km restricted to S. Okay, here you could be a bit like, oh, are you sure about this? Because this is like, you know, this is like I'm commuting operations a bit without saying too much about it. Because here I'm taking the determinant of T star M already restricted to S. But if you write it like this, you're taking the determinant of T star M and then restricted to S, right? But it's the same. It's all the same. It's just a restriction. So you're like the functions are really the same. Algebraically, everything is the same. And this is all defined over M anyway. And then you restrict it to S later. It's really all the same. Like in principle, of course, you could run into the problem that, I don't know, there is another bundle defined globally, which restricted to S is the same. But for that, we don't care. I mean, sure, here instead of Km restricted to S, you could have something which restricted to S is Km, but we don't care for that. Okay, so okay, these are isomorphisms. This one we don't know. This we have no idea what it is. But we do know one thing that we do know is that n S is dimension 1. So this is dimension 1. Sorry, rank 1 again. So the determinant is nothing. Because this is rank 1 and the determinant of something of rank 1 is just itself. And here we have what we care about. So this. Okay. But if you remember from what we did a few hours ago, so, yeah, there you go. The normal bundle to S is this OS restricted to S. So, going back, not the dual. So we multiply. So we have Km restricted to S, tensor NS is isomorphic to Ks, right? So we multiply times NS, and these two cancel out on the right. And now we finally have our Km tensor OS, all restricted to S. Yeah. Question? No? Okay.
No, I was just wondering whether it's important whether it's on the right or on the left, but then I remembered.
No, I mean
about the
it's just
tensor
a,
product. Yeah, it's okay.
yeah, it's just you can just move it to the right, to the left.
Yeah,
This looks a bit better because this is a bundle defined on the all of M, right? This is defined everywhere, and then you restrict it to S. Do you remember? And S is OS restricted to S. And again, restricting before or after is the same. You know? So yeah, this looks. I mean, it has a nice look because it's like you're thinking that this KS as an extension. This extends KS in a somewhat natural way. Okay, so I think this proposition puts together basically everything we defined today from Cartier Divisor, bundle associated to it, and then exact sequences. And it shows how, like, I think this proof really shows the strength somewhat of exact sequences. Okay, so tomorrow we will, sorry, not tomorrow, but next Thursday, we will dwell more with this concept of line bundles. So we will study line bundles and in particular define what is called the Picard group. Because as I hinted today, if you take two line bundles and you take the tensor product between them, you still get a line bundle. And you can think as the trivial bundle as kind of a neutral element and the dual of a bundle as its inverse. So this should already make you think that there is a group structure somewhere. And in fact, there is, and this is called the Picard group, but we'll deal with it next time. And then also next time we will describe the Picard group, so all possible line bundles of the projective space, complex projective space, which is some very big list and important one.